Perfect.
So, Ainara Rodríguez is going to talk to us about ultrashort pulse lasers for battery cells manufacturing. She is a researcher in the Advanced Power Metallurgy and Laser Manufacturing Group at CEIT. She is a Telecommunications Engineer from the University of Basque Country and a PhD from the University of Navarra. And she has been involved in both national and international projects regarding basic and applied science, and has been published all these results in more than 40 peer-reviewed papers and publications. And she is co-applicant in more than 3 papers. And this work that she's gonna present us here has been done in collaboration with Ainara from the center. So, Ainara, I will pass you the role of presenter.
Perfect.
You can move on with your presentation. Yeah, please see it.
Yeah.
Ainara Rodríguez, thank you very much.
Sorry, because
I guess that you are using two.
yes, because I have the 2 screens here, so white would be better, right?
Yes.
Okay.
Perfect.
Okay, so first of all, thanks to SECFA for the invitation to give a talk in this webinar, and also to you, Alex, for your kind introduction today. Also, maybe the title of the presentation seems quite similar to the previous one. I think that even I haven't talked to Miquel Bengoa before. We have made very complementary presentations. So I hope I will tell you something that hasn't been presented here before. So first of all, just 1 minute to introduce our research center. So CEIT is a non-profit research center that was funded almost 40 years ago by the School of Engineering of the University of Navarra. We are located in San Sebastián in the Basque Country, and we mainly develop research projects in TRLs between 3, 4, and 7. We also train young researchers by supervising their PhD in collaboration with the School of Engineering of the University of Navarra, and we are also very involved in the dissemination of knowledge, obviously of the knowledge that we generate with public funding, and not the one with the private funding from for the companies we work with. So just to make a short introduction, Miquel has already told you a few production steps where different laser technologies can make a difference, or at least can make an improvement of the process. Cutting or welding of tabs, different electrodes and different components cutting, different modification or structuring of the electrodes, and also thermal induced drying of the coatings and different parts. But I have to say that every time a laser process wants to go into the industry, it needs to compete with conventional techniques. So to become an accepted process in the batteries manufacturing industry, this should improve or maintain not only cell performance but also the safety of the batteries themselves. So I think these are two ideas we need to keep in mind when developing new laser processes for this specific industry. So in this context, there are very well-established processes based on continuous wave and nanosecond pulse lasers, like some of the ones that the previous speaker has presented. But there are other processes that can benefit from ultrashort pulse lasers. Why? Well, mainly because I'm not going to go into details, but ultrashort pulse lasers are lasers that have very, very concentrated energy and power in terms of pulse duration and also in terms of focusing distance. So we can produce very, very short pulses in the length of hundreds of femtoseconds, that is 10 to the minus 15. So which are the benefits of these lasers compared to other type of lasers? Well, mainly that they do not induce any thermal damage to the surfaces of the material they are processing. And also because they can produce very, very precise structures. So then, which are the main processes that can be suitable for this technology? Where can ultrashort process provide an advantage over laser systems? Well, mainly those that involve materials that can be damaged due to the thermal effects. These are mainly the different polymers and also metals that have very high thermal conductivity. So keeping in mind this and also the two previous control conditions that we have for exploiting lasers in battery manufacturing that need to improve or maintain cell performance and safety. And also that ultra-short pulse laser will make a difference when the materials involved are polymers or metals with high thermal conductivity. We have two ongoing developments in these research centers where laser techniques can make a difference for the fabrication of battery cells. I'm not going to talk about battery packs or the integration of the different cells in the packs, but I'm going to talk about processes applied to the battery cells, so the main component of the battery. So the first of these projects or this development is the structuring of the current and aluminum current collectors for improving the performance of lithium-ion cells. When I say current collectors, I mean that we are not targeting the electrode material itself, as Mikael has presented, but I am targeting the copper and the aluminum current collectors. They are materials with very high thermal conductivity, and also there are very, very cheap materials. So this work that I'm going to present right now has been made in collaboration with SIC Energy Uni, that is a non-profit energy research center that is also located here in the Basque Country, that was founded in 2011 and is one of the most prestigious research centers in energy around Europe. So what are we doing for this application of batteries? So the project we are developing, so the batteries application is one of the applications we are targeting in a European project for the development of metallic functionalized parts. This project has been funded and started 2 years ago. We are targeting 3 different applications. The first one, biomedical implants, in order to improve the antibacterial properties and also to get a better adherence or also integration of the implant. We are targeting the metrology application that is mainly related to improve the diffraction properties of the linear encoders. And also we are targeting advanced batteries by the structuring of the current collectors. That is the work I'm going to present here. So which are the goals for this application field in this project? Well, mainly to reduce the cost of the cells, avoiding chemical treatments of the copper foil. Just mainly try to remove the carbon-coated copper foil and replace it by just a laser-treated copper foil. In this way, we can remove one of the treatments and also the chemicals associated to this coating process. We also think that this process can improve the capacity values and the capacity retention at high currency densities, and that can also decrease the cell resistance and impedance. Additionally, by structuring the current collectors, we can also improve the adhesion between the electrode material and the current collector, so that maybe another process can be removed, or we can improve this adhesion. So how are we going to do this? We are mainly doing this by texturing the metal foils that looks like the 2 rows you have here on the slide. just a very, very thin metal foil, around 10 to 12 microns in thickness. And we produce what are called laser-induced periodic surface structures that are mainly some kind of periodic lines that can automatically be defined in the surface of a material. You can see here in this micrograph, this is the scale bar for the image. This is 1 micron. So take into account that these lines have a period of, let's say, 800 nanometers, are always below the wavelength of the laser we use. So we can produce very, very precise structures in the surface of the metals that can improve the performance of the current collectors. How we do this? Just by scanning the sample with an ultrafast laser. We scan the sample in this way so that we apply different lines to the sample, and these nanostructures are generated automatically. So they are self-ordered. We do not need to move the scan by 800 nanometers each time. So we just write a single line that contains lots of these 800 nanometer lines. And we are applying this to the current collectors, both the copper and the aluminum collector, not only for coin cells, but also for pouch cells that are this second shape of cells you have here. So we can control the type of structures we get in the surface. We can adjust the period by choosing a different laser with a different wavelength. We can produce, you can see here on the right corner of the slide how the current collectors for coin cells will look like. So this is the same material, but just with a short irradiation on top of the surface. So one of the main problems of copper and of metal irradiation of materials is that we can induce some kind of oxidation in the material, and this is something that is not a good point for the fabrication of batteries. But we have seen that we can control the degree to which the copper is oxidized by adjusting the process parameters. So you can see here these graphs are the vertical axis is the oxygen content of the surface of the material after laser irradiation. You can see here that depending on the fluence, that is mainly related to the power of the laser, and to the number of pulses that is related to the scan speed or the process speed, we can have different oxygen contents for different conditions. Take into account that these are the values that we get for copper, but if you compare them to the ones we get for stainless steel or titanium, these are much lower for many of the for most of the process conditions. So it is a good point that we can control the geometry of the structures we produce on the surface, and that we can also do it without a significant amount of oxygen content for the subsequent processes. So what can we do? How can we, what have we obtained with these current collectors? Well, we have fabricated current collectors with different laser conditions, and we have tested them into the electrochemical equipment that are provided by Thick Energy Union. You can see here the results they have obtained. The image in the left side is are for different samples processed with different conditions of the laser. So we have samples with different names for different speeds of powers of the laser source, and you can see here how they behave as they are cycled. So for those of you that are not familiar with this type of graphs, this is mainly related to the speed of charging and discharging of the batteries. So C/10 means that it takes 10 hours to charge the battery and 10 hours to discharge it. And this number means that is 1/10 of an hour to charge the battery. So this means a fast charge, and this means a low speed charge. So it is important to remark two things here, mainly what is the capacity, so the initial value here, and also what is the capacity retention. The ability of the cell to recover the initial capacity that it has before it starts to be cycled. So you can see here that depending on the processing conditions, we can get different curves for this charging and discharging, and for the capacity and capacity retention. The best one here is the one that is marked in the red. That is the one corresponding to the sample E. That has a very very good capacity retention and very good capacity values at the starting of the cycling process. And if we compare this behavior of the best of the conditions we have obtained with what is the standard for cell manufacturing, we can see here this is just the copper foil, so a standard copper foil without any modification and without any carbon coating on top of it. Then we have the green one, that is the one corresponding to the copper foil with the carbon coating. That will be the, let's say, the standard for the batteries manufacturing. And then we have also the sample we have obtained to behave the best. And also another reference for the same material we have used for the current collector. So you can see here that the capacity retention of the electrodes that are processed with the laser have the same capacity retention as the carbon coated foil. So we could replace the coating process by a laser process. And you can also see that we have a better capacity value for this laser processed carbon collector than for the one with the carbon coated, that is, let's say, the standard or the target for this application. So by inducing these structures on the surface, we can get better capacity values as well as maintain the capacity retention of the standard or the today used technology for this fabrication of batteries. And I will try to be very brief because I'm sure we are out of time, but I would like to present you also another development we are performing here that is mainly related to the fabrication of sensors for improving the safety of battery cells. So today, one of the main limitations of the monitoring of the batteries is that it cannot be done in all the cells that make part of the battery pack. So there are thousands of cells inside any battery, and there are very few available technologies that can be used for developing sensors and to monitor the individual cells. When monitoring the cells, two of the main important parameters are the temperature of the cell and also the deformation, because this means that there is something happening inside the cell that can be destroying the battery or can make it go down in performance. So we have developed two different types of sensors for the measurement of the temperature and the strain or the degradation of the battery. And we have done it on the pouch material, so that like the bag where the cell is contained. This is a polymer material. So again, we are targeting one of the applications where ultrashort pulses can make a difference. That is targeting polymer material because they are very sensitive to thermal effects and to other types of lasers. And we are also trying to go for improved safety of the batteries. So the different sensors have been printed not only in non-preform pouches, but also in preform pouches. You have here the sensor is this small part. You can see here on the right side of the slide. There is a sensing material with a specific geometry. And these big lines you can see here are the metallic connections in order to extract information from the sensors to the outside connectors. And well, we are quite happy with the results we have obtained for this. So the sensors have a quite good TCR value for the temperature monitoring. but we can also somehow check what is the cell voltage, the state of charge, and also the state of health of the battery according to the deformation sensor we have developed. So you can see here how the sensor is working. This is the strain sensor working as a function of the different. So we can measure. Sorry. The voltage of the cell related to the information that our sensor provides us. So you can see that even there is a parallel evolution of both lines. We cannot directly detect what is the state of charge, but we can see this linear trend here, and if we get the area that is covered by this linear trend, we can estimate not the state of charge, but when the end of charge process is happening. So we cannot detect how it's been charging, but we can detect when it has finished the charging process. And also there is a strong correlation between the degradation of the signals of the degradation sensor and the state of health of the battery. So you can see here that for, I think these are 58 different charging and discharging cycles. You can see that the values that the sensor provides have a very strong negative correlation with the state of health of the battery. So we can use the different values we get from sensors, that's maximum, minimum, or average strain values. We think that the maximum is easily detected under normal operation conditions, but we can also use the minimum and maximum and average strain measurements. So this is just an initial some initial results for the sensing technology. And if you need further information on any other questions, because I've gone very quick in order to fulfill the time requirements, you can ask any of the researchers in this slide. I am responsible for the laser processing of materials here in CEIT together with Iago Laizola. Dr. Isabel Ayerdi is in charge of the development of the sensors for monitoring battery cells. And Miguel Ángel Muñoz is in charge of the electrochemical performance of the battery cells that have been structured using lasers. So any questions related to the electrochemistry of the batteries or the performance, please refer them to Miguel Ángel, and the rest of them you can contact either Isabel or me, that we will be very happy to answer to you.
Okay, thank you very much for the very interesting presentation. I have a very fast question, probably very brief, regarding let's say the resolution that you have with the lasers you use.
Yes.
How well can you? So what's the minimum resolvable feature that you can tackle with your technique?
So for the self-organized structures, usually the resolution you get with this technology is around 0.8 the wavelength of the laser you are using.
Okay.
So we have got some structures of, let's say, 200, 250 nanometers using 400 wavelengths, and we used to obtain like 700 to 800 nanometers for 1 micron wavelength. So that depends on the wavelength you are using. You can slightly tune them by adjusting the laser parameters, the scan speed mainly, but it is in that order of magnitude.
Okay, I see. So it's wavelength dependent, and it's
yes.
with the diffraction limit. I understand. Okay.
Yes.
So thank you very much again for your presentation, and
You're welcome.
we'll probably move to the next one.